Welcome to another chapter. This time it's pure chapter 2 from year 13 Edexcel A-level. It's functions. So what we look at here in this chapter is the modulus function, the domain and range of functions as well. So we take some ideas from year 12 and extend them further. So some of this you will have seen before, some of it, most of it of course not. So let's have a look and explain together what's in store for us in chapter 2. Before we have a look at the chapter 2 specifics, of course, I do normally give you some warm-up questions. Here they are. There's 4 to try this time. So pause the video now would be my suggestion. Try these on your own, on your note paper. And when you're ready to see the solutions, press play and I'll guide you through them and hopefully we'll agree. Okay, so assuming you've had a go, let's have a look together at the solution to warm-up question 1. So in warm-up question 1, we have to solve 16 to the x plus 1 equals 8 to the power 2x plus 1. The thing we need to spot here is both of these values, the 16 and the 8, are both powers of 2. So we need to rewrite the 16 and the 8 in terms of powers of 2. So 16, I'm going to rewrite that as 2 to the power 4. I'm going to put it in brackets as well. So I've got 2 to the 4, and all that is being done to the x plus 1. That'll be the same as 8. But 8, of course, is 2 cubed. So if I rewrite 8 as a power of 2, 2 cubed, then I'll see that's 2 cubed to the power 2x plus 1. We now need to remember some laws of indices. So we've got powers next to powers, so we need to multiply these together. So 4x plus 1 gives us 4x plus 4 for the new power of 2 on the left. On the right, 3 times 2x is 6x. 3 times 1 is 3. So we can see here the base values are the same for both to the power 2. One side's equal to the other. The only logical conclusion we can make is that the powers must be the same. So therefore we can conclude that the 4x plus 4, this particular power, must equal this power here. The next thing is just a fairly simple solving process and then we're good. So talking you through it anyway. Get the x's onto the same side, so subtract 4x from both sides of the equation. That's going to give us 4 equals 2x plus 3. Now what I can do is I can subtract the 3 from both sides, so knock off 3, which is going to give me that 1 equals 2x, or in other words, 2x equals 1. Therefore, dividing by sides by 2, x must therefore equal a half. If you want to check in your calculator, you can do. 16 to the power 1.5 will give you the same as 8 to the power of 1. 2.5. Question 2. We have this equation here, a quadratic in terms of x squared. So we've got kx squared minus 2x plus 3 minus 2k equals 0. We're told it has equal roots, so that's a big clue. So equal roots is a tip that we need to be thinking of what property of a quadratic tells us how many roots it has, or types of roots, and that is using the discriminant. So you need to remember what the discriminant is. The discriminant of a quadratic, which you can use a symbol delta as well if you're lazy like myself, is b squared. I'll explain what a, b and c are in a moment, so this is just a recap in case you've forgotten, minus 4 multiplied by a multiplied by c. So to explain in alphabetical order, that a is the coefficient of the x squared, so our a in this case is k. B is the coefficient of x, so the x stuff we have here is minus 2 lots of x, so the coefficient of x, b, is minus 2. And c are all the constant terms. So I have a constant 3, and k is constant because it says, so minus 2k is a constant. So 3 minus 2k combined is also just another constant. So all of this is our c. We then need to recall that if it's got equal roots, then the value of a discriminant will be equal to 0. Exactly. So if a quadratic has 2 distinct roots, the discriminant is greater than 0. Equal roots, which is the same as saying one repeated root, or just one root which is the same but twice, discriminant's equal to 0, and if a discriminant is less than 0, we have no real roots. But because it's got equal roots, that's when we know to set it equal to 0. So we just plug in what we know and solve. So b squared, for us, that's going to be k squared. Whoops, what am I talking about? So b is minus 2, of course. So we've got minus 2 squared minus 4 multiplied by a, which is k, multiplied by c, where c is 3 minus 2k. So all of that we set equal to 0. So we need to do a bit of expanding now. So minus 2 all squared is 4. Minus 4k multiplied by 3 is minus 12k. Minus 4 multiplied by minus 2 is positive 8. And k multiplied by k is k squared. Set that equal to 0. Now if you notice, you could actually do this on the calculator now and just solve using the calculator function. I'm going to do it old school because it looks quite nice and solvable. What's brought my attention here is that all these terms are divisible by 4. So we can divide both sides of this equation by 4. That'll then give us 2k squared minus 3k plus 1 equals 0. So then you need to convince yourself this will factorise into 2 brackets. So I'm going to do my method quite quickly. So I'm going to just think of 2 times 1 is 2. So 2 times the n number. Think of it like this. Equals 0. That 2 will come back in a moment. 2 numbers that multiply together to make 2, but add up to minus 3. That's going to be 2 and 1. Then this 2 now I'm going to put back in underneath the values like that. Now if I was to factorise it and bring these numbers up to the front after simplifying the fraction, but because I'm just solving, I can leave it like this. So therefore, k, to make this bracket equal to 0, k would be positive 2 over 2. In other words, k would be equal to 1. Or to make this bracket equal to 0, because we've got one bracket multiplied by another equaling 0, k would have to be positive 1/2. So those are the 2 solutions that would work for where k gives a quadratic which has repeated roots. Question 3 is just some coordinate geometry to revise. So we've got a point M, which is k, then 2k is its y coordinate, lies on the line with this equation, x minus 3y plus 15 equals 0. Find the value of the constant k. So there's a couple of ways of doing this, but I think probably the most elegant way is to just spot what this coordinate means. The point M is just the point where whatever x is, the y coordinate is double that. And so what we can do here is sub in that, well, x is obviously k and y is 2k. So we're going to substitute in, instead of x being k, well, x is k, and we're going to substitute in that y is 2k as the expression for y instead of just y itself into this equation here, because the point M has to satisfy that y is double the x coordinate at the point M. So using this setup, this equation here becomes k minus 3 lots of 2k plus 15 equals 0. So expand this out. We're going to have k minus 6k plus 15 equals 0, minus 5k plus 15 equals 0. Add 5k to both sides, so 15 equals 5k. Finally, divide both sides by 5. Therefore, k must equal 3. And again, if you had time in an examination or test or whatnot, do verify it if you can, something quite simple like this. If you put 3 in for k, so m should be 3 and 6, and so if x is 3 and y is 6, that should work. So 3, take away 3 times 6, 3 times 6 is 18, 3 take 18 is minus 15 plus 15 is indeed 0, so it does check out, which is always a relief. Finally, for the warm-ups, warm-up question 4. We have a curve C with equation y equals 2x cubed plus 5. The curve C passes through the point P with coordinates 1, 7. We have to use differentiation from first principles now to find the value of the gradient of a tangent to C at the point P. So differentiation from first principles. Now, you are given the formula for this in the formula book, but the process is fairly long-winded. I'm not saying it's hard, but you need to follow it step by step, and some students forget the steps. So just to aid your revision and to make sure you're getting all the steps, let's start off from the right point. So for this one here, what do we start off with knowing? Well, in the formula book, we're told that the gradient function is defined as the limit as h approaches 0 of the function with the input of x plus this dummy variable h minus the value of the function at f of x, all divided by h, imagining that as h shrinks down to a limit of 0, the value of this limit is our gradient function f dashed of x. This is the derivative. So here, our f of x, our input, we just basically take the input. F of x is 2 lots of the input cubed, so input cube it multiplied by 2 plus 5. So f of x plus h is going to be, this is where people can get confused as well, so we call f of x 2x cubed plus 5, so essentially our input goes there. So f of x plus h, I'm just going to switch the x for the new input x plus h. Now just as we squared just the x, but all of the x, here we just square the brackets x plus h, but all of it. So that's our expression for f of x plus h, which we need to use here. So, substituting those expressions in, f x plus h being replaced with this, minus f of x being replaced with 2x cubed plus 5, all minus, gives us this. So, this is really important that we have this step in place. I've put big brackets around the f of x plus h to separate it nice and clearly from minus f of x, to try to avoid the confusion with minus and pluses going everywhere. So, first of all, we've got an x plus h cubed, so this needs to be expanded. So we can either do this the slow way by doing x plus h, x plus h, x plus h, and write that out 3 times. What I'd suggest we might want to do, though, is remember the binomial expansion from year 12 and those patterns. So I'm not going to dive into the binomial expansion and go 5 minutes explaining that again, but using the binomial expansion or otherwise, expanding this out, you should get this as your next step. So all I've done here is expanded out x plus h all cubed to arrive at this. So 2 lots of x plus h all cubed is the same lots as 2 lots of all of this in brackets. Still got the plus 5 there tagged on the end. I've left the f of x minus for now, because I still need to expand all by 2. Inside these massive brackets, I've got these little ones, which need to just expand by 2 first. So doing that first of all gives me this, and then I can then combine things and see clearer now what to do. So looking at this line here, I've got 2x cubed here, but I'm taking away 2x cubed over here. So I can cancel off 2x cubes. Then I've got plus 5 minus positive 5. So in the same way I can cancel the 5s. So cancel the 5s and cancel the 2x cubes, just make things easier. And then group together things what you can on the next line. But in fact, there's nothing really to group together. So the next line, I've just got 3 terms on the numerator, all over h on the denominator. And it's really important that I must stress, even though you're just doing the same thing, simplifying each time, you need to put lim h going towards 0 at the beginning of each step of your working. Without putting lim h going towards 0, h arrow 0, you will lose marks. So you need to be formal. This is a formal process, differentiation from first principles. So next line, just basically this one neatened up a bit. We have this. So we can divide through all of this numerator by h. So 6x squared, h divided by h, that will just give us 6x squared. 6x h squared divided by h will give 6x h. 2h cubed divided by h will give 2h squared. So we now have this. Now we can see clearly what's going to happen is h goes towards 0, 6x times nothing, essentially, will become nothing, and two lots of something which is approaching nothing times something else which is approaching nothing will, in the limit of that thing becoming nothing, become nothing. So these two last terms cancel to just leave us with just simply 6x squared. So in the limit, these last two vanish to give us the limit, which is simply 6x squared. So therefore, when x is 1, we can just substitute in the gradient of a tangent. The gradient function at 1 is f dashed of 1, which is 6 times 1 squared, because x is 1. 6 times 1 times 1 is 6. So we differentiate from first principles there, then apply it quite easily as the last part. So let's get into the main topic now, which is about these functions. The first function we're going to talk about is the modulus function. So first of all, yeah, fair question, what is this? Well, the modulus, also known as the absolute value of a number, x, is written as mod x, basically two vertical lines either side of a variable. So this is how it's written. So it's like brackets, but vertical lines rather than curved lines. So this is pronounced mod x, or sometimes modulus x. Mod x is probably me being a bit lazy and colloquial. Anyway, what is it? What is the modulus? It's essentially the distance of the number from 0. It's its absolute size. So you can think of the mod of x as the non-negative value of x. So for example, the modulus of 5 is 5, because 5 is already positive, and the modulus of minus 7 is 7, because a modulus basically doesn't allow anything to be negative, so it makes the minus become positive, so the modulus of 7 is 7. Another way of thinking about it is the distance of minus 7 from the origin is 7, because it's 7 to the left of the origin. So more generally and algebraically, it can be defined like this. The modulus of x we can summarize piecemeal. So it's defined as being x itself is if x is at least 0. However, the modulus of x becomes minus x in the case of the input into the modulus x being less than 0. In terms of function notation, the modulus of f of x is f of x itself if the value of f of x is at least 0, or is minus f of x where f of x is ever less than 0. Like I've said before, the modulus will always return a positive value. So generally, a modulus function is written in the term y equals mod f of x. That's the most basic form of a modulus function, and ones we're going to see a lot through this chapter. So first of all, let's just, before we do the harder questions, let's have a look at some rudimentary applications of what this modulus function does. So let's introduce a function f, defined as f of x is the modulus of 2x minus 3 plus 1. So that plus 1 isn't being modulused. Okay, that plus 1 is on its own. We're not taking the modulus of plus 1. We're only doing the modulus of 2x minus 3. So a, b, c, we need to evaluate f of 5, f of minus 2, and f of 1. So first of all, a. If our input is 5, we're now going to do the modulus of 5, which is 2 lots of x, so 2 lots of 5 minus 3 plus 1. Treat the modulus as brackets, so do the brackets first when simplifying. So 2 times 5 is 10 minus 3. So it's a modulus of 10 minus 3, then plus 1. But 10 minus 3 is 7. So it's a modulus of 7 plus 1, but the size of the number 7 is just 7 itself. So that becomes 7 plus 1, which of course is 8. So f of 5 returns a value of 8. Now, same idea, but now our input, our x is minus 2. So this time, f of minus 2 will be 2 lots of minus 2 minus 3, modulus of all of that, then plus 1. So let's simplify what's inside the modulus first. Well, 2 multiplied by minus 2 is minus 4. Still got that minus 3 after, then plus 1 after the modulus. Inside the modulus, minus 4 minus 3 becomes minus 7. So we've got the modulus of minus 7 plus 1. The size of the number minus 7 is positive 7, so this line becomes positive 7 plus 1, which again gives us a value of 8. So the function f of x returns a value of 8 at both f of 5 and f of minus 2. For part C, f of 1, exactly the same idea. You might be able to do this one yourself. If so, try it now, then play the video when you're ready to see it. In any case, f of 1 will be 2 lots of 1, because now x is 1. 2 times 1, minus 3, all modded, plus 1. 2 times 1 is 2, minus 3, plus 1. So in the modulus is 2 minus 3, which is minus 1. The modulus of minus 1 is 1. So it simplifies all down to just simply 1 plus 1, which of course is 2. So that's how we do it simplistically. That's how you do it without graphing it. So let's have a look at some harder functions which might involve doing graphs of modulus functions or solving, perhaps using a graph sketch. So sketching modulus functions. There's at least 2 approaches. I say at least 2 because I never pretend to know every single way. There's 2 ways I know. One way I generally prefer over the other, which I'll mention in a second. Anyway, 2 approaches to sketching these graphs as modulus functions. So let's just consider a fairly basic example. Y is the modulus of 2x plus 1. So approach A, this isn't my favourite, but it is for some of the teachers. Horses for courses, whichever way works for you, go with that way. So approach A, what we do, we just remove the modulus signs and just consider the function as just honest to God, just basic 2x plus 1. So what's a basic y equals 2x plus 1 function look like? So we sketch this, pretending it wasn't a modulus function at all. I hope you agree that's what it would look like. Gradient of 2, y-intercept of 1, and then of course, if you wanted to work out the x-intercept, sub in when y is 0, x would be minus a half there. So that's your first step, it's sketched. Step 2, you need to remember that the modulus always returns a positive value. So anything underneath the x-axis is not allowed, because this is negative, but a modulus function has to return a positive value. So what do we do to get round that? Well, step 2 is quite simple. All we're going to do is any bit of a graph which lies below the x-axis, we're going to reflect that section of it in the x-axis. So this portion here underneath the x-axis, I'm going to ghost it, but imagine each section of this just reflected up the same distance away from the x-axis on this side, it's going to appear on the other side. So it's going to go like this. And so then what you'd be doing is sketching on like so, and then neatly with a rubber, because obviously we always draw in pencil, don't we? If not, neatly rub out at the bottom. That's step 3, which you're not actually explicitly wrote down. So step 3 is remove anything below the x-axis. That's what you're left with. So a neater version of what I've tried to show you here, you should end up with something like this. So on the right hand side. So the second approach, otherwise known approach, B. So begin with the parent function y equals mod x. The parent function has nothing to do with biology. What I mean by parent function here is the most basic function type that fits what this function is doing. So basically, is it a squaring function? Is it an exponential function? Are we doing a natural log? This main thing it's doing, the beast of the function, is it's modulating. It's doing the modulus of an input. So the most basic form of this is mod of the most basic input we can have with algebra, just call it an x. Okay, so the parent function here is y equals mod x. In the same way that if we had a quadratic, x squared minus 7x plus 71, the most basic parent function from a quadratic would be y equals x squared. Anyway, enough of that. So begin with the parent function y equals mod x. So it's a symmetrical v at the origin. So that's our y equals mod x. Now we're going to get from the most basic type of mod function, and following the correct steps, we're going to end up with this more complicated mod function, whichever one we happen to be wanting to actually sketch. So starting from this, what are the steps? So step by step, it's very similar to BIDMAS with a couple of exceptions. So what we do first in the second step is we're going to go from the most basic parent function, which is y equals mod x, to arrive at y equals whatever we want. So I've broken it down into 4 different constants. So it could be something more complicated, where we could have at least 4 different numbers to contend with. There could be a multiplier at the front of a modulus. There could be something multiplying or doing something to the x. There could be a coefficient of the x inside the modulus function. There could be a constant, plus or minus something inside the mod function. Then also, we could be adding or subtracting something at the end as well, which isn't anything to do with the modulus itself. So we need to do this in order. Like I said, it's very much like BIDMAS. So, like BIDMAS, we think of the modulus symbols, these vertical lines, as brackets in their own right. But remember, when we're doing translations of graphs, inside brackets works as opposite. So brackets, yes, we do those first, but because it's inside the brackets, it works opposite to what normally would happen. And so normally, in the brackets, you'd obviously do the adding before multiplying by b, because BIDMAS multiplying comes before addition. But because it's inside these mod symbols, we do it the opposite way around, so we deal with the c first. Inside these, it works opposite. So we're going to deal with the adding c first, which actually works as subtracting c from our x values, because again, inside opposite in that way too. The second step, we then deal with the second part in the brackets, well not brackets of course, the modulus symbols. We deal with the b, and it looks like x is being multiplied by b, whereas actually, inside opposite, instead of multiplying by b, we divide all x values by b. So the x coordinates get divided by this constant in front of the x. Once we've dealt with the brackets, we can then step outside of them. So then BIDMAS goes in its normal order now, because now, dealing with the b and c, we can now do BIDMAS as it normally would happen in the real world. So we've only got the a, which is multiplying, and then an adding of d. Well, m comes before a in BIDMAS, because now we're not dealing with these modulus things anymore. It's now common sense. So we deal with the a first. That a is on the outside of the mod brackets, so it's just dealing as it looks. So it's a multiplying by what we just had there. So the y values get multiplied, get stretched by that a factor. Then finally, we add d onto whatever y value we had. So the final thing to deal with is any number on its own. That's a vertical translation. We just add d onto the y values. So we follow these steps absolutely religiously, and we can't go wrong. A final point about this BIDMAS rule: the order of operations is the same as BIDMAS, treating what is inside the modulus as being inside the brackets. But again, the usual order inside the modulus is reversed, inside as opposites. So inside the modulus symbol, remember you'd do the adding bit before multiplying, and rather than actually adding on to your x values, actually minus that thing from the x values. Rather than actually multiplying by b, we're dividing. So by b, yes. So we've got y equals mod x. The first thing we've got here, we've got a is 1. Basically, we don't need to worry about a. There's no number in front of a modulus symbol there. We've got b is 2. We've got our c is 1. So we deal with c first. So we're going to minus c from the x values, which means we're going to take that 1 and not add 1, but rather take 1 away. So our v is going to move 1 to the left, like this. So now we have y equals the mod of x plus 1. So this here is going to be at minus 1, and this y-axis intercept will be positive 1. Now we can deal with this 2, so that 2 isn't going to multiply the x-coordinates, it's going to half them. Remember, inside is opposite. So that minus 1 will become minus a half, and because y values aren't affected by that, that y-intercept will stay as 1. So finally we have this. So 1 is unaffected, but the x values get halved, so we get minus 1 half here. So even minus 0.5 as a decimal. Don't know why I put it as a decimal, I'd normally put a fraction. So this or minus 1 over 2. Now, let's try another one. So this one I've made harder, as you can see, more complicated. So let's sketch the graph of a function f of x is 3 lots of a modulus of 0.5x plus 2, n modulus, then all that minus 1. So I put the sections in here to build a step-by-step process for you, like a flowchart almost. You can pause the video now and have a go yourself if you'd like, or if you want to, press play and then I'll guide you through how I'd probably think about doing it. So, first step, parent function. So let's just get our coordinate axes in first. Our parent function, y equals mod of x. Just a symmetrical v, like so. The first thing we'd do is deal with this 2. Okay? So in our case, we've got a, b, c, d. So we deal with the modulus symbols first. But remember, inside opposite, we do the adding or subtracting first before dealing with the coefficient. So x plus 2, but inside opposite, rather than adding 2 to the x, we're going to take 2 away. So our v shape is just going to move 2 to the left, like so. So this is now minus 2, and this bit of the graph is going to be positive 2. So, the next thing. We've done the plus 2 part. We've still got some bits inside the modulus symbol to contend with. We need to now deal with this 0.5 part. So we're now going to go from y equals mod of x plus 2 to y equals mod of 0.5x plus 2. So the 0.5 isn't going to multiply x by 0.5, it's going to divide x by 0.5. Dividing by 0.5 is the same as multiplying by 2. Remember, inside, opposite. So we're going to double the x coordinates that we know. So minus 2 will now map to minus 4. 2 will be unaffected because 2 is a y coordinate. So essentially it's going to get stretched outwards and will look something like this, with this being minus 4 and this still being at a height of 2. So we've dealt now with inside our modulus symbol. Next we step outside. Outside of it, normal rules apply and common sense of vidmass does. So now we're going to multiply by 3, then do the minus 1 after. So after doing the modulus of 0.5x plus 2, now consider going from this to y equals 3 lots of a modulus of 0.5x plus 2. That 3 is outside the modulus symbol, so it doesn't affect the x, it affects the y values, and because it's outside the modulus symbols, it affects in a common, obvious sense way. It looks like we're multiplying the mod by 3, and that is exactly what we do. So we just simply take our y values and triple them. X values are unaffected. So that 2 is now going to go to a height of 6. Minus 4 will stand put because that's an x value, and this bit here will equally be tripled in height, in steepness. So it looks something like this. Minus 4 will still be there. 2 times 3 becomes 6. So minus 4, 6. The final step now is this minus 1. That's outside the modulus symbol, so it affects y only in a common sense way. So the whole of the y values get dropped by 1. So this v shape here just gets moved 1 unit down on the y-axis. So this minus 4 point here will still be minus 4, but will be at minus 1 for y. So that's minus 4. That's 6. Now goes 1 lower to a 5. And that point there, it was where on the x-axis, now it's where y is minus 1. So, how do we solve modulus equations? Well, a carefully constructed graph can be used to solve modulus equations. However, extra care is needed when sketching the graph to make sure that f of x is reflected in the x-axis by the modulus function when f of x is less than 0 at the correct coordinates. So your sketch is crucial. I'll also mention how to do these if you want to without using a sketch as a backup method, but also you might find it a slicker method and, dare I say, slightly more sophisticated, but it's slightly more advanced. It's only when you get more confident with how the algebra of the modulus function works. So I've put in this box here how we would do it, just algebraically, not graphically. So generally speaking, if we've got an equation, mod of something equals something else, mod A equals B, the solutions are when A itself is positive, just simply A equals B, or if A were negative, the mod would force it to be positive by multiplying it all by a negative. So you also need to consider when minus whatever's in the mod equals b as well. So I'm going to show both ways, the graphical way and algebraic after. I'm also going to marry up two as well. Hopefully you'll see why this algebraic way works, so you can see from the graph why it is this case. Because this is just like, trust me and see for now. After you see the graphs, hopefully it will become more crystal clear. So first worked example, let's solve this equation. When is the modulus of 2x minus 1 equal to 5? So graph sketch. So I'm going to show you two different graphs. I'm going to put in blue the graph of this modulus function, and then in green the graph of y equals 5. So first of all, the parent function start with y equals mod x. Then we can go from y equals mod x. First of all, we need to do y equals mod of x minus 1. Okay, remember that 2 comes after. Inside the modulus works as opposite. We deal with the minus 1 first, but rather than minus 1, we add 1 to our x coordinates, that inside opposite thing yet again. So this value here is going to be at 1, and this one here, this y-intercept will be at 1 as well. That y-intercept will be 1 in case you're wondering, because here, that is where y equals x minus 1. This would have been negative, but the modulus has multiplied it all by minus 1. And so what's happened here is it's been basically changed from x minus 1 to 1 minus x. X times minus 1 becomes minus x. Minus 1 times minus 1 becomes plus 1. So that intercept just becomes plus 1. So we've done this part now. We now need to think about going from this to y equals mod of 2x plus 1. That 2 doesn't multiply the x coordinates by 2, because inside opposite effect, we're going to halve the x coordinates by 2. So the next step is half the x coordinates. The graph is going to get stretched inwards by a factor of 2. So y equals mod 2x minus 1 looks like this. X values get halved, so 1 goes to a half. That 1 is unaffected. So now we can add in where y is equal to 5. So the two solutions are given by this point here and this point here. So hopefully you can see it's basically going to be where 2x minus 1, this is a graph y equals 2x minus 1. Where does 2x minus 1 equal 5? This point here, that's the graph of all this multiplied by minus 1. So solving for this coordinate would be where minus 2x plus 1 equals 5. So essentially what we're going to do now, I'm going to do it together, is we need to solve this. So either 2x minus 1 is 5, which is that coordinate, or minus 2x minus 1 equals 5, which is that one there. So let's get going. So let's do this one first. So add 1 to both sides. We get 2x is 6. So therefore x equals 3. Or of course, this other solution, let's pick a different colour, let's go for purple, is given from this one. So minus 2x minus minus 1 becomes plus 1. So I'm making a pig zero of this. Don't make it as messy as me. I'm going to add 2x to both sides. So 1 equals 5 plus 2x. Subtract 5 from both sides. 1 take away 5 is minus 4. And dividing by 2, x must be minus 2. So either x is 3 or x equals minus 2. Those are the two solutions for worked example 1. Second worked example. Solve mod of 3x minus 5 equals 2 minus a half x. We can again use a very similar approach to worked example 1. So again, in blue I'm going to put the modulus function. In green I'm going to put the non-modulus function, y equals 2 minus a half x. So let's build our sketch of y equals the mod of 3x minus 5, starting from our parent function, y equals mod x as shown. The symmetrical v, y equals x on the right, y equals minus x on the left. So are we going to do the 3 first or the -5 first? You should be hopefully able to see yourself now what we do first, predicting. If you thought, well, I'm going to deal with that -5 first, great. And then if you remembered, but rather than -5, we're going to add 5 onto the x values instead, that's fantastic. So let's do that now. So let's add 5 to the x values. So the v goes from the origin to where x is 5, y 0, and this one here, that y-intercept is now at a height of 5. Now we can deal with this 3, so rather than multiplying the x values by 3, because we're still inside the mod symbol, so inside opposite, we're going to actually divide our x coordinates by 3. Y coordinates are unchanged, so 5 will stay at 5, but this point here will go to 5/3. So our v is going to become bent inwards, made steeper at both sides symmetrically. So y equals mod of 5x minus 3 will look like this with these axes intercepts. We can now add on the graph of y equals 2 minus a half x. So remembering from GCSE, this will just have a gradient of minus a half, and we'll cross the y-axis at 2. So it will look like this. And because the y-axis intercept is 2, we can label on that it crosses obviously at 2. And then we can solve for when 2 minus a half x is equal to 0 to find the x-intercept. So if 2 minus a half x equals 0, we can hopefully see that x would be equal to 4 to make that equal to 0, because 2 take away half of 4 is 2 take away 2, which does give 0. And so this x-intercept here is going to be 4. So now we can see we're solving for these 2 points here. So this point and that point. So seeing how it just boils down to this rule algebraically in this box, we're solving for when y is 3x minus 5 hits 2 minus a half x. And for this one here, where v is on the opposite branch, this is when we've got y equals minus 3x plus 5. So this point we're solving minus 3x plus 5, this whole thing made negative, equals the green 2 minus a half x. So we're still solving, essentially, these two things. So that's what we're going to do together. So first of all, let's do this one. I'll color code this one in red. So this top one. So if I add half of an x onto both sides, so 3 plus half of an x is 3.5 of an x, which I'm going to call 7x over 2. So 7 over 2x minus 5 equals 2. If I add on 5 to both sides, I get 7x over 2 equals 7. So therefore, if then I multiply by 2 and divide by 7, you'll see hopefully that x has to be equal to 2. So one point it's solved is where x is equal to 2 itself. And then solving this one here, which let's go for purple. This one, by making it all minus, becomes minus 3x plus 5 equals 2 minus a half x. Now if I add 3x to both sides, that gives me 5. I'm not writing this out very well, folks, I do apologise. It should be nice and neat, one line, then another, then another. Been a bit scratty. Please forgive me. Anyway, I then have 5 equals 2. Then minus a half plus 3 is 2.5. So that's going to become 2.5 x's. Sorry, 5 over 2x. So then subtract 2 from both sides. So we get 3 equals 5x over 2. Then multiply by 2, divide by 5. Therefore, we have x equals 6 over 5. So our two solutions, x equals 2, or x equals 6 over 5. Slightly different, but more or less the same really, to be fair. Solving modulus inequalities. So this process is largely the same as before when dealing with inequalities. Although many modulus inequality questions can be solved without a graph in theory, knowing how to construct a sketch will save you from having to remember the below. So it works with very much the same though, so there's not much new, there's nothing new in fact to remember. So in general, when dealing with equations of a type mod of something, any inequality symbol there meant something else. The solutions are given by thinking of when is a thing being modded positive, when is it its normal self, then whatever symbol you're dealing with, less than, equal than, b, or think of it when a itself would have been negative. Modulus would have then made that minus, so when minus whatever might be negative, same symbol, whatever. So I'm always saying, like, I'm not being explicit with the symbol because this symbol can be anything. So whichever inequality symbol, keep it exactly the same. So for example, I could have done like 5 different lines. One line with that symbol, copied it again with that symbol, same rule for that symbol, same rule for that symbol. So it's whatever the symbol is, just keep it exactly the same, facing the same way around. So let's have a look at how that works with an example. So this one, solve when 5x minus 1 is greater than 3x, when the mod of all that is greater than 3x. So again, sketch it out. Parent function first, y equals mod x. Now we can transform from y equals mod x to the mod of x minus 1. That minus 1 is what we deal with first, inside opposite. Rather than taking away 1, we're going to add 1 to the x-coordinates, so we get this here. Now we can go from mod of x minus 1 to the mod of 5x minus 1. That 5 is inside the mod symbols, so inside opposite. So rather than multiplying by 5, we're going to divide the x-coordinates by 5. Y values are unchanged, that will set at 1. That x point there will become 1/5. So the v gets bent inwards like so. We then can think of what the graph of y equals 3x looks like. Well, hopefully you'll clearly know that it's got a gradient of 3 and a y-axis intercept of 0. It's going to go through the origin. So if we add this on now, we can then think about how that looks as well. So there we have it. So now we're solving clearly. This bit of the this bit of the blue rather, is where y equals 5x minus 1. And so we're wanting where 5x minus 1 is greater than 3x, or the blue is also higher than the green over here. And this blue line here is the graph of y equals this whole thing made negative. So y equals minus 5x plus 1. So this solution is where is minus 5x plus 1 greater than 3x. So the two inequalities we're solving here are these two. So doing it together, let's have a crack. So having a crack at this question. So that bit in yellow is one where it's higher than 3x. So let's consider this one as the first solution. So if I add 1 to both sides, if I now take 3x from both sides, I now have 2x. So there we have x divided by 2. So one solution is x greater than a half. And the other one is this bit here, which is going to be given from solving this bit. So if I just make some space. So minus 5x minus minus 1 becomes plus 1. And I'm going to add 5x to both sides. So on the left, I'm left with just 1. 3x plus 5x is 8x. Finally divide by 8. So x needs to be less than 1/8. So therefore the solutions of that inequality, putting those two together, I'd say x or x. And that solves for that one. So now it's over to you to try some of these on your own. So in the blue book, in your blue books, it's too early in the morning, turn to page 26-27, have a go at exercise 2A in the Edexcel book, I'm suggesting to try questions 2, 4, 6, 8 and 12. So I'm liking the even numbers today. Try more if you can, and always check out the extension questions. In addition to what I've said today, Desmos, or in fact any decent graphing software on an app or a PC or laptop is your friend. I like Desmos, but there's also GeoGebra and all sorts. So use the technology there to help you see these sketches in a richer way. Keep plugging away, keep going at it hard. Let me know if you get stuck. Thank you once again for listening. I'll see you all very soon.